All right, so this is section 4.1, exercise 8. We're given a function that models the velocity of a toy rocket fired vertically from the ground on a calm day. So we're assuming it's going to fly vertically. At what time after the rocket is launched does the rocket's velocity equal 0? So we're going to call that time A. So we're given a velocity function, and we want to know where that equals 0. So we can take the expression of our velocity, 500 minus 32t, set that equal to 0, and start solving. 32t equals 500, which means that t is equal to what? I'm getting 15.625 seconds. So we'll call that A. This time value when the rocket's velocity reaches 0. What happens to the rocket at time equals A? So if its velocity, its vertical velocity goes to 0, that's basically when it has come to an instantaneous rest. It has risen to a certain height, stopped, and now it'll start to come down and accelerate downward. Well, it's been accelerating downward the whole time, but it's going to start to move downward. So that's part A. Part B, find the total value of the total area enclosed by y equals vt and the t-axis. Okay, so we want to find an area under a curve, so let's graph this curve between this time t equals 0 and t equals a. So here's 0, time axis, this is measured in seconds. This is the velocity axis measured in feet per second. All right, so I know that initially my velocity is 500 feet per second. And I know that at some time, what was it? 15.625. 15.625 seconds, it decreased to 0. So my curve plot across this point here, this point here. Can I just join those points with a straight line? I think looking at this graph or looking at this equation or this expression tells me that that's linear, so I can join them with a straight line. So there's a graph, and it wants me to find the area under this curve. So how do I find this area here? This is a triangle. Better yet, it's a right triangle. But how do I find the area here? The area is equal to 1/2 times the base times the height. What is the base? The base is 15.625 seconds. And what is the height? The height is 500 feet per second. So if I multiply all those things together, I get 3,906.25 what? So the units are what? I have feet over seconds multiplied by seconds. That should just give me feet. So what did this area give us? What this tells us, it gives us a position. We took a velocity equation, a velocity function, and we found the area underneath that function with respect to time. So what we found is a distance. Specifically, it's the upward distance this rocket travels before it starts to come back downward, or it's the maximum height of this rocket. A lot of ways to express what's happening here, but they all kind of describe a position of this rocket. Part C, find an antiderivative S of the function v. So we've been doing derivatives all class long. Now we're taking your derivative rules and kind of, turn them around. Instead of finding a derivative function, I'm going to give you a function, and you find me a function whose derivative is that. So, just like with derivatives, we can take this a term at a time. First term is constant. What kinds of functions have derivatives that are constants? Well, those are linear functions. So specifically a function with a slope of 500. So I'm going to say that 500t is my first term. Another thing I'm going to point out here is that essentially the power rule that we've talked about for a long time. So what's the derivative of x raised to the power of n? So where x is variable and n is a constant exponent. This is one of the first, if not the absolute first rule that we talked about, is this derivative here. So what if we were to go the opposite way? So what's the right way to talk about this? What do we do here when we take a derivative? Well, we do two things. First, we multiply by n. So we basically, you might think of bringing down that n, but we're multiplying this term by the exponent n. And then what's the number two thing we do? We reduce exponent by 1. So now we want to do an inverse thing, which means we're going to take these two steps, we're going to do them in the opposite order, but we're also going to do the exact opposite of those steps. So our second step was reduce the exponent by 1. So we're going to do that first. And what's the opposite of reducing the exponent by 1? We are going to increase the exponent by 1. And then step 2 was our original step 1. We're going to multiply by the exponent n. So now instead of multiplying, we're going to divide by the exponent. What's the exponent though? The exponent is going to be not n, but n plus 1. So just to be sure here, what happens to x to the power of n? Well, we're going to increase its exponent, x to the n plus 1, and then we're going to divide by that exponent. And just to be sure, we're probably very comfortable with derivatives, especially compared to doing antiderivatives. Let's take a derivative of x to the n plus 1 divided by n plus 1. So if I have x to the n plus 1 over n plus 1, when I take a derivative of this thing, I'm going to multiply it by n plus 1. And then what am I going to do? I'm going to take the exponent and subtract it by 1. So the n plus 1 cancels this n plus 1 denominator. These ones cancel. And what I have left is x to the n. So now that we understand, or now that I've explained that, I don't want to assume that you're understanding on the first time we go through this. It's going to be a little bit hard, or a lot harder, to redesignate these derivative rules and kind of go the opposite direction with them. So now I want to take the antiderivative of negative 32t. So that would be negative 32. I want to increase the exponent by 1, so it becomes t squared. And then I want to divide that by 2. So this becomes 500t minus 16t squared. So I think this is a good antiderivative. Maybe let's be totally sure though. We're told that if we take a derivative of this, that should equal the velocity. So what is the derivative of 500t? That's 500. What is the derivative of negative 16t squared? That will be negative 32t. So I think that's a good check. This is exactly what we started with as our velocity. All right, part D. Compute the value of s of a minus s of 0. Okay. It might not be a surprise what we're going to get, or maybe it is. So let's do this. What is a? 15.625 minus s of 0. We said s of t in general was what? 500t minus 16t squared. So what is s of 15.625? That's equal to 500 times 15.625 minus 16 times 15.625 squared. I'm getting a number that seems a little bit familiar. So this comes out to be 3,906.25 feet. So what does that number represent here? Well, we found a position function. So this is the position of the rocket, or more specifically, the vertical position, the height of the rocket after 15.625 seconds. S of 0 is the position of the rocket initially. So the position of the rocket at 0, which suppose we should find. What is S of 0? S of 0 equals 500 times 0 minus 16 times 0 squared. That is 0. So from time equals 0, so from our initial launch to 15.625 seconds later, the rocket had changed in height, changed in vertical position by 3,906.25 feet. And part E, compute S of 5 minus S of 1. What does this tell you about the rocket's flight? So let's do that. What is S of 5 minus S of 1? So S of 5 is equal to 500 times 1 minus 16 times 1 squared, which is 484 feet. And then call that S of 1, do the opposite thing. What is S of 5? S of 5 equals 500 times 5 minus 16 times 5 squared. Right. All right, I'm getting 2,100 feet. So what is the difference between these two values? S of 5 minus S of 1 equals 1616. What does this number tell you about the rocket's flight? Well, the last question told us, so in a span of 15.625 seconds, so the entire upward flight of the rocket, it increases in height by 3,906 feet. But in this 4-second interval, early in the flight of the rocket, it travels 1,616 feet, which is not quite half of this. What does that tell you about the rocket's flight? Basically, its position is going to be changing more rapidly in the first half of the flight. And if you've ever seen anything like something in free fall, if you throw it upwards, its motion is fastest at the beginning. And then its motion slows down until it comes to that peak, until it comes to that instant moment of rest. So one more way I can start this or illustrate this is look at this graph here. Can I pluck out here where 1 and 5 are? So 5 seconds will be about a third of this interval. And then 1 second will be about here. But if we look at this as an area under a curve, there's much more area here, for example, than there will be over the next 4 seconds because the rocket is starting to slow down. So very early on in the rocket's flight, it's going to be covering more distance. Its position is going to be changing more rapidly. That's why you see that, over this 16-second flight, if we just take a 4-second chunk of that early on in the flight, you're going to be covering, proportionally more position, more distance.